In this example, we're given some properties of a function. We're given the critical points and we're told where the first derivative is positive and where it's negative. And the first thing we need to do is classify the critical points as either local maxima, local minima, or neither. Okay, so let's first of all draw a number line like we've done in the past. Okay, I'm just going to draw a little line here. And I'm going to mark the critical points at 2 and at 5 because that's what we're told. Those are the critical points. And so now it says f prime is positive to the left of 2. Okay, so for points less than 2, f prime is positive. That means the slope is positive. So I'm going to draw an arrow with a positive slope. And to the right of 5. Okay, so for x greater than 5, we also are told that the derivative is positive, right? So the value, the function has a positive slope when x is greater than 5. And then we're told that f prime is negative between 2 and 5. Okay, so now we have our little number line, and now it's easy to classify those critical points, right? Because you can see now that we have a local maximum at x equals 2, and we have a local minimum at x equals 5. Okay, just based on the first derivative test and the information that we're given. All right, and then our next task is to sketch a possible graph of f of x. Okay, so now I'm just going to draw axes here. Okay, let me draw that. Okay, I'm going to draw axes here. Now, there's the issue I have is that I do not know what the y values are. Okay, so I'm just going to have to, let's see, this is x and this is y, but there's no good way to tell what the y values are. I don't have enough information. But this number line with the arrows gives me a really good the start of a picture of what this function looks like. So I'm just going to put a scale here. 1, 2, 3, 4, 5, right? So there's 5, there's 2. Those are our critical points. And I know I have to have a local maximum. So I'm just going to mark some point as a maximum. And then I know I have a minimum at 5. So maybe it's there. But I don't know. I don't have enough information, but it's got to be, if it's a minimum, it's obviously lower than the maximum if it's a continuous function. And so now I'm just going to connect these up so that I have a graph of, that matches. I have to match the slope, right? So, the graph of f of x has a positive slope, right? Because the derivative is positive. The derivative is positive, so the slope is positive, which means the original function f of x is increasing. And then it decreases, right, until you get to, let me try that again. It decreases until you get, okay, should do this offline here. Until you get to 5, right, and then again the slope is 0, right, because it's a critical point. And then it increases again, right? So maybe it looks something like that. All right. So this is a graph of f of x, right? I was given information about the derivative and the critical points. And so now what I've done is work backwards to find the general shape of the graph of f of x. Now, again, I don't know what the y values are, right? So I could have something maybe that looks like this, right? It could look like this. It could have a minimum. Let's see here. It could come down, have a minimum here, and then, it could look like that. It has I got the general shape, but I don't know the y values. So, so this is just a sketch of the general shape of the function. And but this is not a unique solution. So maybe I'll make a note of that. This is not a unique solution. Okay, but it just gives us the general shape of the graph of f of x. All right, I'll meet you in the next video.